All right, recorded is rolling. It is Monday, September 19th, and there's been testing going on the last few days, so I haven't seen you guys at all since last Wednesday. Remember where we left off is, uh, well, we just started on courses on Newton's laws of motion, dynamics. I had you guys do these 10 mini labs, and then debrief most of these with you guys. So you guys were had these spring forces in your hands and some weights and some other objects. We're seeing all different which ways that forces could work. Right. So yeah, just started on that. Let's see where we are here. Oh, let you guys know. Yeah, today's picture day for your English classes. Maybe some of you guys had pictures already. So yeah, there you go. I did post that on Friday afternoon to Google Classroom, so hopefully caught you guys there. So for something good to school. There were a bunch of top scientists on projectile motion. I knew I had that paper printed out and must have left it at home. So I have to bring that in tomorrow. Last Thursday and Friday, again, I did not see you guys, but with your covering teachers, I left some material. So I do want to recap that real fast, just in case you were testing or didn't have an opportunity. So I gave you guys some animation flip books, so you guys could apply your physics knowledge of kinematic motion, plus your own imagination, and make a flip book. There are a bunch of really good ones. I have just a few within reach right now, so take a look at these. Guy with bow. Okay. Now, what I really like about this one is that it demonstrates a projectile. Look at that. Like if you want to have an animation that your brain can believe, like, oh yeah, like your brain's like, yeah, I can believe that. It looks pretty realistic. Then you have to have frame by frame where each picture of each arrow would go. Okay, figure out where it's going to be vertically, horizontally. Okay. See, we got water droplets. Okay. It's one of your conceptual questions. What happens to water droplets? Like, okay. Pretty cool. Then there's got a beam. Bing, bing. Yay, that's fun. So a lot of fun ones, a lot of really good ones. Okay. The other thing, well, one of the materials I left you guys with your covering teachers were these analog calculators. You guys had a template and a paper clip. So if you want to see the full demonstration explanation how this works, I made a recording back on Friday, so you can catch that in Google Classroom. But I'll give you guys a quick rundown. So suppose it's back in the 1960s, and you guys are engineers working on the Apollo mission, and you're trying to send astronauts into space. Do you have one of these scientific calculators conveniently in your pocket? Ooh, because these digital calculators don't exist yet. Well, you kind of sort of do, but they're like the size of an entire room, and you probably have to very patiently put in calculations one by one, right? You can't just whip this out of your pocket because it doesn't exist. Okay. So they were doing calculations all the time, probably doing a bunch of stuff on paper, but what kind of calculator did they actually have? You guys have heard of a slide rule? Slide rule? Okay. It looked like a ruler, but it would like slide against itself. Okay. But if you look really close on that slide rule, the numbers were not evenly, they were not spaced linearly like they are actually on this ruler. It's like there'd be a huge gap between the 1 and 2, and then the gaps would get smaller, 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 right? And then small gap between like an 8 and a 9. Right? Now they would use that to multiply, divide, take square roots. How can you do that just by sliding two rulers against each other? Well, this right here is a version of that. It's just turned into a circle, which actually has some advantages. So it's arguably a slightly better design even than the linear version. Okay? So once you got the parts clipped out, you take the paper clip, punch it through the middle, okay? And then you can, rotate the circles like this relative to each other. Okay? Let's take a look at these circles. So you guys see, oh, look at that, a huge gap between the 1 and the 2. Then between the 2 and 3, you get a smaller gap. Then the 3 and 4, you guys see the gap's getting smaller, smaller, smaller between each pair of integers. Okay. And then, okay, we've got 8, 9, 9.5, 9.9, and then 1. So we're back around 1. Interesting. Okay. So these numbers are actually scaled logarithmically. Okay. And since it goes 1 through 9, and then 9.9, and then back to 1, this 1 might represent a 1, but it might represent 10, 100, 1,000. The key is you're going to have a floating decimal place. So you allow the decimal place to float. Okay? Now, remember, you can rotate these two circles with respect to each other. But one thing you can do is line up all the numbers. Right? So 1 and 1, 2 and 2, 3 and 3, so on all the way around, right? So you guys see that? Okay. Now, what if I start rotating them relative to each other? What if I do this? Pick my go-to example here. Okay. So I have the inside one aligned with the outside 3. Again, if you have the slide rule version of this, it'd be the same thing, just like all on the line, but here's a circle version of this, right? Okay. Now, one thing you'll notice is that, we're just let me give you guys a little more context. 3, outside 3, inside 1. Let's treat that as a fraction, like 3 over 1. Can you guys imagine that could be a fraction, 3 over 1, right? Okay, now, one thing that you'll notice is that all the way around the circumference is the exact same ratio. Okay, so 3 over 1 is equal to 6 over 2 is equal to 9 over 3, right? You guys see it's the same. Right? You can pick any pair of numbers all the way around. It's still a 3 to 1 ratio. It's always 3 to 1. Okay. How about right here? 1.2 over 4. Ooh, wait, does that break down? 1.2 over 4? But remember, all these numbers have a floating decimal place. So 1.2 might actually represent 12. And 12 over 4, that's still 3. Okay. So is 15 over 5. Okay. Yes, that so still works. Just let the decimal place float. Keep track in your mind what that would be, right? Okay. Now, if that's true, could you guys set up fractions that are equal to each other? In fact, they're all equal all the way around, right? Okay. So 3 over 1 is equal to 6 over 2. In fact, if you didn't know what 6 over 2 was, I mean, obviously you do. It's a really simple example. Okay. Then since 6 over 2 is equal to 3 over 1, well, 1 is the denominator, doesn't really change the numerator, so it just points to the answer, doesn't it? And the answer is just 0.3. Right? It's like the pointer. Is that? Right. So now you can divide anything. Right? Let's come up with some crazy numbers. What is 93 divided by 24? I don't know. 93 over 24. Okay. Now in my mind, I'm gonna say that's probably about 3 or 4 somewhere in there, right? Versus, I know it's not like 30 or 40 or 300 or 400. It's about 3 or 4. Right? So let's see. So 93 and 24. So take the outside 93, which is bam right there. Inside 24, rotate it. Bam right there. Okay. Now those two are aligned exactly where they need to go. Right. Remember, the inside 1 points to the answer. Right. In fact, it's pointing a shade less than 4. It's like 3.9. Looks like about 3.9 or so. Right. Let's see what this is. Oh, 3.87. Ooh, look at there. Look at there. So now you guys can divide anything. Do you know what else you can do? You can also multiply anything. Because you guys remember cross multiplication? So let me go back to my kind of simple setup. Here it is. 3 over 1 is equal to 6 over 2, right? Remember that? Well, 3 over 1 is equal to 6 over 2. Then I can take advantage of cross multiplication. And this, whatever is above the 1, this 3 times this 2 is equal to this 6. Right? In fact, I can multiply anything by 3 with this configuration. 3 times 1.5 is 4.5. 3 times 3 is this 9. Okay? So now you can multiply and divide. Okay? So one last thing you can do, which is you can take roots. Okay? Now this, you don't need both circles. And just to emphasize that fact, I'll pick this apart and just look at one circle. Okay. Square root, for example. Guys, what's the square root of 4? 2, right? So here's how we're doing square roots on this thing. Okay, so find my 1. Okay. Find my 4. I want to take the square root of 4, right? Now 1 is like home base. You do that, right? Now you guys just told me, or wait, let me ask you guys another question. Okay. What is a square root as a power? That's 1/2. It's a 1/2 power, right? Okay. Now remember, these numbers are scaled logarithmically, right? So we're gonna go halfway from 1 to 4. What's the halfway journey? Like take this path all the way around, right? And bam, right here, it's 2. Is that? How about this? What if what's halfway between 1 and 9 logarithmically? Another way to say that, what's the square root of 9? 3. Let's do a journey around. What's halfway between these two? 3. How about this? What's the cube root of 8?
It's 2.
It's 2, right? Okay. A cube root. What is that as a power? It's a third, right? Okay. So if I split this journey into thirds, okay. So first third, second third, third third, right? What's under the first third? Remember my red thumb? Bam. It's 2. Is that? All right. So now you guys can do multiplication, division, and roots with a couple pieces of paper. Have fun. Mystery Cup Challenge. I know some of you guys already know how this works. I've been asked by my classes earlier today, and they wanted another day to think about it. So I'll give you guys another day too. Right, again, some of you guys already know the answer. But remember, this cup has a couple holes in it. I fill it halfway with water, keeps all the water, fill it to the brim, and the entire cup drains. The question is, what's going on inside this? You guys take another day to think about that. We'll revisit that another day. All right, and then all right, here's what's taking rest of class today. We'll do this real fast, and then we're going to do a bunch of free body diagrams. Today is a good day to be taking a bunch of notes. So Newton's laws of motion. These are on the back of. You guys remember this table packet? There's a bunch of conceptual questions. All right, all these materials on Google Classroom. I'll have spare copies up here. Okay. So there are these 3 laws of motion that will govern everything in the universe. Well, until we get to like relativity, then it's masters on these. Hopefully you guys learned these in a science class maybe back in middle school, and this is just review, but let me pause this recording. All right, recording resume. All right, here we go. All right, so the first law of motion is also called the law of inertia. Have you ever heard that? Law of inertia, Newton's first law of motion, same thing. Right. An object at rest will stay at rest. So this guy right here is not just going to spontaneously jump off the table, unless there's an outside force acting on it. Right. So the only reason it would be starting from rest is if I push on it with a force, some force or pull. And an object in motion will maintain its velocity. Now you guys know that velocity has 2 parts to it. It's speed, which is the magnitude, and also direction, right? So an object that is in motion will maintain speed and direction, again, unless there's an outside force acting on it. So my classic go-to example is the Voyager spacecraft. So back in the 1970s, actually there were a couple sent off. So say Voyager 1 spacecraft, it was launched. It's been going since the 1970s, just decades it's been going. It's like at the edge of our solar system right now. Right? But what's keeping it going? Like, does it have like a bunch of fuel, right, that's been like blasting its engines for like several decades now? No, it's just inertia, right? It's been in motion. It's just going. Maybe it's a tiny gravity force from the sun, but it's just going, right? It's just going. Right? Once they had set to escape speed from our solar system, just fly off forever. And so there you go. Now your car might be a different story. If you take your foot off the gas pedal, it'll eventually slow to a stop. But for the same reason, it still fits within this context because there are frictional forces acting on the car that slow the car down, right? But if you get out into deep space, you can see some really good classic examples of these things, right? Okay. Newton's second law of motion. Right. So this one, I think the best explanation is the equation form. Most textbooks you see it written as F equals ma. Now that F refers to a net force. Right? I prefer the fraction form of this. Right? But what does Newton's law's second law of motion say? It says what causes accelerations. Right? So you guys know what acceleration is. Acceleration is a rate change of velocity. And you guys have done some measurements with the car and ramp lab. You guys have done some labs, incorporated a bunch of calculations about acceleration. But now we're getting to the part of the class that says, well, what causes accelerations? Because I know from the first law of motion that nothing ever wants to accelerate unless there's a force. Okay? So now here's the equation that relates to that. Okay? Now, an object might only have, or actually it can only have one acceleration. It can't have multiple accelerations. It might have multiple forces acting on it. Like this object right here, I have several forces acting on it right now. Okay? There's a weight and a normal force, and also I'm pushing on it with a couple of forces. Okay? But it can only accelerate in one direction at a time. Okay? So really, it's the net force that matters, right? The net force. Okay. So if I did something like this, maybe I could add the forces together, do something like this, maybe do some Pythagorean theorem, right? Something like that. Okay. So this one says the acceleration of an object is directly proportional to the net force acting on it. So if you triple the force, you're going to triple the acceleration, but also inversely proportional to its mass. Acceleration is, right? Acceleration and mass are inversely proportional. And you can see that very clearly with this fraction form. So if you triple the mass of an object, you get a third of the acceleration, right? Have some math, like make it triple the mass. For the same force, it's not going to accelerate as much, right? If you push on the entire Earth, right, hardly accelerates at all. Right? Guys get that? Okay. And then, of course, force and acceleration are both vector values, so will also have the same direction as each other, right? Acceleration will be in the same direction as the net force. And then the third law of motion, this is the equal and opposite rule. For every active force on object A by object B, there is a reactive force equal in magnitude and opposite in direction on object B by object A. A version of that. Right? So if you ever push on something, you will get an equal push back, right? You have to. There's never been any exception to this, right? If you push on any object, there's always an equal and opposite force back the other way. Okay. Guys got that? Guys got Newton's laws of motion? All right, guys ready for some free body diagrams? So free body diagrams, I introduced this idea to you guys last week. So now let's do a whole PowerPoint on this. This will probably take a couple of days, but we'll do as much as we can today. Free body diagrams. So remember what the definition of this is. It's just a diagram showing all the forces acting on an object. You guys probably remember that from last week. Right? So what you're going to do this is draw force vectors to represent relative magnitude and direction of the forces. Right? So you have an example up here on the side. Now, if you ever just draw an object with only its weight acting, like right there, would that be a scenario like, for example, you go to the edge of a cliff and just drop a rock, right? That could be what that is, right? It could be free fall, right? It could be free fall.
If it was in a vacuum.
Yeah, in a vacuum. True. Yeah, in a vacuum that'd be true, right? Right. How about this? What if you throw the rock off to the side and it's already left your hand and it starts to go into a projectile motion again in the vacuum? Would that still be that situation? Yeah, sure would, right? Because remember, all you care about is the forces, right? Now, well, what's this whole thing about the relative magnitude, blah, 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 right? Well, let me throw in another force here. So the weight is acting down. That's what mg is, right? Mass times gravity field is the weight of an object. Right? Told you guys that last week too, right? Look at this force vector that's acting upward, F sub n. That stands for normal force. Now, to know what the normal force is, from a math class, guys, if two lines are normal, that means they're what compared to each other? Perpendicular, right? So normal force, perpendicular to what? Right. So let me flip my screen over, show you guys perpendicular to what. Let's see. Okay. So this way right here has two forces acting on it right now. In fact, you just saw the free body diagram for it. It has a weight pulling down. That's the gravity force from the earth. Right? Most of the time I label that mg, just like I did on that slide, mass times gravity field. But you could also do F sub g, gravity force. Right? Okay. And then there's also a support force from the surface. See, if there wasn't that support force, it would just be in free fall, wouldn't it? Right. But this is clearly in equilibrium. Right? It's not moving. Right. So there's zero acceleration. There's zero net force. Do you think it's a support force from the table holding it up? Right. In fact, since the table surface is itself horizontal, then wouldn't that support force be vertical? That would be perpendicular to that, wouldn't it? Right? See, if I do something like this, like if I put this on an incline and start going like this, right? Ignore the fact I'm holding it. Suppose it's like a rigid incline, right? That support force from the surface is still perpendicular to the surface, right? In fact, it gets less and less the more you tip it up like this. You can kind of see that in that poster over there above that door right there. We're eventually working our way towards that, but might not get there exactly today. Okay. All right, so you guys know normal force is a support force from a surface, and it's always perpendicular to that surface. Okay. As I said for AP here, this is just a convention that I picked up from them, but actually I like this convention anyway, so I use it. So connect the tail of the vector to the center of mass and draw the force vector extending away from the object, exactly like that picture shows, right? So I got this object that's blue, and do a black dot to represent the center mass, and I'm drawing all the force vectors extending away from that center mass dot, right? So that's just one convention. I like that convention, so I use that myself. Okay. Because what are forces measured in? What unit? Newtons, right? So when you're drawing force free body diagrams, remember the kind of vector that you care about. Do you care about velocity vectors? No, you do not. Do you care about acceleration vectors? Do you care about momentum vectors? Do you care about displacement vectors? Do you care about force vectors? Bing! Those are the only vectors you draw in free body diagrams. Okay. Now, sometimes I'll draw a directional arrow to indicate velocity only because something like friction force or drag force always opposes the direction of motion. So you might want to know for context direction of motion. But besides that, I only care about force vectors. Okay. And forces are measured in newtons. Okay, you guys got that? Okay. All right, so block at rest on a table. So here's how we do this. I'll flash you guys a scenario and give you guys a moment to draw that in your notes. If you guys can beat me to the answer, if you can draw it in your notes before I reveal the answer on the PowerPoint, then that is a good indication that you know how this works. Now this one you should definitely get because you just saw the answer last slide. Right? You guys got the weight acting down and the normal force acting up. Boom, block it rests on a table, done. Okay. And notice how those are also labeled, right? So if I give you guys a quiz here in a week or two, and I ask you guys to draw some free body diagrams, and we're taking a couple of days to do these, this might be pretty important, then you guys know you're going to draw only force vectors, you're going to draw them extending from the center mass dot, and you're going to label them. Okay. There are different labels that'll work. So mg, mass times gravity field, that represents the weight. You could label it weight. You could do F sub g, force due to gravity. Right? And then F sub n is the normal force. Boom, boom. Right. You guys good there? All right, next one. Suppose that there's, again, a block at rest on a table. But what if somebody's pushing on it with a small horizontal force, but not enough force to overcome the friction between the block and the table surface? What's that going to look like? Right? So got that object sitting on the surface, come across it, give it a small push, but it's not enough to break the friction, so it's still just sitting there. Oh, yeah. I'll try and see what you get. All right. Yeah. Okay. Got the idea. All right. Your best chance here. This PowerPoint is posted to Google Classroom, so you want to go back and access it that way too. All right. So did you guys draw? Remember to connect these to the center of mass dot two, right? The weight acting down. Right? I mean, if you don't have that, then kind of hard to have very much else just floating around. Right? There's the normal force that will always balance that out. Well, in this case, I guess always is a dangerous word, right? Right. So you're pushing on it with an applied force. Right? Now, if I just drew that and I walked away from the paper, would that be right or not? It would not be. There's a mismatch between that diagram and that description. What's the mismatch? Oh yeah, true, friction. Right, friction. Yeah. Yeah, so friction is true. That's a good answer. Also, you guys see that at the very beginning it says block is at rest. Right. Now that diagram with those three forces, could that ever be at rest? No, maybe you can make a case if it's like turning around or something, but it would have to be accelerating, wouldn't it? Right? Now, how is it accelerating? Just exactly what I have drawn for the free body diagram, right? Well, there's one of two things that could be happening. It might be moving to the right, speeding up, or it might be moving to the left, slowing down, right? Could it be like moving to the left and you're pushing it to the right and so it's slowing down, right? And which one of those it is actually ambiguous. You wouldn't know, right? But let's make this diagram match that description. I still need one more force. Bam, friction. And if you got it exactly right, see how the friction is exactly balancing the pushing force, right? That would mean that all the forces balance. There's zero net force. See how the verticals cancel and the horizontals also cancel? Okay. And if there's zero net force, that means there's zero acceleration. If there's zero acceleration, well, that's one possible example of how it could be at rest, right? I mean, at rest, it is an example of zero acceleration. Right? How about that, right? All right, while you guys are finished, copy that down and digesting that, here's some more details about friction. You guys see that friction force right there compared to that normal force? Right, now, kind of off at a skewed angle here. But see how I drew the friction force as smaller than the normal force? That's almost always true. There are a few exceptions to that, but that's almost always true. Right. Now, suppose that you are pushing harder. So the harder you push, that friction force automatically responds and builds up. And suppose it's just at the tipping point where if you pushed any harder, it would break the friction and start sliding. Right now, it's not sliding yet. It's not moving. but if you put like 1 more micronewton, it would, right? So it's just at the tipping point, right? So like friction is like maxed out. You guys get that concept, right? So you max it, right? Right. If you take that maxed out friction and divide by that normal force, and just eyeballing it from my kind of skewed point of view, I'm gonna, let me ask you guys, because I think you guys have a better perspective. If you had to estimate what's the ratio of friction force over normal force, what do you think that would be? What to what ratio? Maybe like 40%, maybe 50%, somewhere there, right? For my point of view, maybe I'll call it like 0.4, like 40%. Maybe suppose this is like 40% of this, right? That ratio has a name in physics, and it's called the coefficient of friction. And if it's specifically in the case where you have a maxed out friction force and it's not broken friction yet, it's called the coefficient of static friction. So that'll eventually come up again in this class, right? Friction force over normal force is called the coefficient of static friction. And that value is a material property between the surfaces. So different surfaces will slide it with different pushes, right? Suppose you have like a wax paper surface or a carpet surface or a sandpaper surface. So I'm going to work differently, right? Okay. All right, guys ready for the next one? Suppose there's a block on a table and you're pushing it horizontally so that the block moves with constant velocity across the surface. So now it is moving, just constant velocity. Did you guys draw a weight and a normal force? Can at least have those, right? Oh yeah.
So are those, the weight and the normal force, are they like always gonna be there, but something is like sitting there?
Yeah. There you go. Right. Yeah. If it's free falling through the air, then it would not have the normal force, right? Yeah. Yeah, so I guess that's true. Like anything on Earth is going to have the weight for sure, right? So there's some like weight pulling on it, right? Yeah, maybe if you went into deep space, you wouldn't have that weight component, but yeah, anything on Earth is going to have the weight. Yeah, if it's sitting on some kind of surface, there's going to be that normal force pushing up, right? We'll eventually get at inclines. You guys see that poster above the door up there shows like a block on an incline. Won't quite get there in the PowerPoint today, but and we're also pushing this thing, right? Pushing it. Right? So I got to throw in the pushing force, right? Okay. Now, if I just drew those vectors and walked away, would that match the description? Or am I missing something?
Missing friction.
Ah, you guys are right. I do have to have friction because of this bit right here. See where it says constant velocity? Okay, guys, constant velocity. What's the acceleration equal to?
Nothing.
Ah, 0, right? If there's 0 acceleration, there's 0 net force. So there we go. So I put the last one you guys need right there, friction force. Right? Is that block in equilibrium? Yes, because the net force is 0. If the net force is 0, acceleration is 0. Those are the same thing, by the way. Right? They go hand in hand. Right? Then that is equilibrium. Right? 0 net force, 0 acceleration. Now you might be, how many of you guys are looking at that thinking, huh, that looks exactly like the last free body diagram. Right? If I go back to the last slide, it looks identical. Sure does, doesn't it? Right? Maybe a slight twist on this, which is that once the two surfaces are sliding past each other, that's no longer a static case, that's a kinetic case. Right? So maybe the magnitudes of these forces would change slightly. But otherwise, besides that, it looks identical. Right? In fact, now the ratio of this friction force to this normal force, now that the two surfaces are sliding past each other, that's still coefficient of friction, but now it's called coefficient of kinetic friction. Right? So this divided by this. Right? And it turns out that coefficient of kinetic friction is always a little bit less than coefficient of static friction. So static friction was like 0.40, coefficient of kinetic friction might be like 0.30 or something like that. Okay, good. A block on a table being pushed horizontally so that there is a net force. There is a net force. All right, so you guys drew a weight vector. You guys drew a normal force. Did you guys draw an applied force? Either F sub applied or F sub push. Actually, that right there. If you just drew that and walked away from the paper, would that satisfy that condition written in white?
Yeah.
Yeah, that actually would do it, wouldn't it? Right. You guys ever played air hockey? Air hockey? Right. Yeah, maybe the normal force I could replace with like force from the jets of air. And that could basically be that, couldn't it? Right. That might right there might be the free body diagram of like while the what's that thing that you hold on to kick the puck? I forget what the thing's called. Anyway, you're holding like some handle thing, right? You bam, right? So while you're hitting it, that might be that free body diagram right there, couldn't it? But maybe yours looks a little different. Maybe you actually threw in a friction force, right? But importantly, see how the applied force is greater than the friction force, which means there's a net force. Okay, so that's like net force going on right there, right? So is that block right there in equilibrium? It is not. It's not in equilibrium because there's a net force. So it is accelerating. Right? Ooh, which way is it accelerating? To the right. Right. In fact, I do know specifically it's speeding up to the right. How do I know it's speeding up to the right and not slowing down to the left? Because friction always opposes the direction of motion. So I know that not only is it accelerating to the right, but it's also moving to the right because it's friction is opposite of that. Right. So I know it's speeding up going to the right. Okay. A rock in free fall with no air drag. Just a rock in free fall. Which has been our go-to assumption, right? For how free fall works. There's no air drag. Right, you guys got the rock and free fall? Did you guys draw a weight? What else did you guys draw? Ah, there you go. Nothing else. That's it. That's the answer. That's the whole thing. Right? Anything in free fall. That's the only force. Okay. Now let's do a rock and free fall. But let's also consider that there's been air drag building up. So if there is an atmosphere, there is air drag. Right? Oh, do you guys see this last detail I wrote? It says before terminal velocity. Guess what is terminal velocity?
Maximum speed in free fall.
Maximum speed in free fall. Yeah, when you do have air drag, right? Now, what do you think air drag is related to? Like if you drop some object, say off the edge of a cliff, right, and air drag starts building up, do you think the density of the surrounding air has something to do with air drag? Yeah, do you think there's a lot more drag in the water than the air? Ooh, yeah, because water's more dense, right? How about the surface area? Do you guys think surface area matters? It's probably why you'd want to wear a parachute if you jumped off yourself, right? More surface area, right? Do you guys think speed matters? Like the faster it's falling, the more the drag picks up? In fact, what if it falls so fast that the drag picks up so much that it matches its weight? That would put it in equilibrium and it couldn't speed up anymore. Okay. That's what terminal velocity would be. So what you guys are doing right now is actually before it reaches that scenario. So it's starting to pick up air drag, but maybe not terminal velocity yet. Okay. Did you guys draw a weight and a drag force that's less than that weight? You guys did that, right? Okay. Let me walk through you guys verbally. Let's get an estimate what the acceleration of that object here is, right? Because the acceleration would not be the full 10 meters per second squared anymore, right? It's going to be less than that, but it's not zero yet either. It's not 0 meters per second squared. Okay. So let's suppose this object had a mass of 1 kilogram, right? 1 kilogram, like your heaviest lab weight, 1 kilogram, right? You drop that off the edge of a cliff, right? And it has a weight of how many newtons? Guys, what's 1 kilogram times 10 meters per second squared? That's 10 newtons, right? 1 kilogram weighs almost 10 newtons at the surface of Earth, right? Usually round it to about 10. Okay. Let's suppose it's been building up to like 5 newtons of air drag. Just eyeballing those force vectors. That might be 5 if that's 10, right? Newtons. Right? Guys, what's the difference between 10 down and 5 up? 5, right? 10 minus 5 is 5. So do you guys see a net force of 5 newtons on this thing? Right. Now let's kick over to Newton's second law of motion, which is put it on that packet or it's on that poster right there. Newton's second law of motion. If you have a net force of 5 newtons acting on a mass of 1 kilogram, what's the acceleration? What's 5 over 1? 5, and then newtons per kilograms goes meters per second squared. So wouldn't this be accelerating at half the rate of gravity? You guys get that? All right. Next slide. How about a rocket? Okay, it's in free fall. Let's also consider air drag. Let's take it all the way to terminal velocity. Now it's remember still accelerating. The last slide it looked like it was accelerating about 5 meters per second squared. Right now, which means it's still picking up speed. Right, but now it's picked up speed all the way to the point that the air drag has built up so much that it can't speed up anymore. What does that free body diagram look like? Yeah. Yeah.
Still has a velocity of downward. It's just not accelerating.
Exactly. You guys catch that? So it should have a weight down and a drag force up, and they are exactly balancing. Okay. Now they're not balancing because of Newton's third law of motion. Right. In fact, I'll tell you what the third law force pairs are. So the equal and opposite force, according to Newton's third law of this weight, is that rock pulling up on the entire Earth. Okay. And the equal and opposite force of this air drag pushing the rock up is the rock pushing against the air down. Right. So these forces being equal and opposite is not because of Newton's third law. It's just they happen to be because that would put this rocket to a state of equilibrium terminal velocity. Right. It's built up to speed so fast that it can't speed up anymore. So the drag force can't build up anymore. Right, you guys got okay now? Right. Now let's do this. I'm gonna flip the screen over and we're gonna do a graph. Actually, we're gonna do paragraphs. Pair of graphs. So let's do these side by side here. Okay, let's do our regular free fall with no air drag next to a free fall situation. But let's consider air drag. Okay. And you guys know we've been doing V versus T, or sorry, X versus T, V versus T, A versus T. You guys know that? Okay. Let's just focus on V versus T for this these graphs. Okay. Let's do velocity in meters per second as a function of time in seconds with no air drag. Okay. Now this one everybody should get because we've done this a bunch of times over the last 2 weeks. Okay. At 0 time, let's say you just released it. Okay. Edge of the cliff, just drop it. As you're dropping it, how fast is it moving? Like 0 meters per second. So this point exists at least, right? Bet you guys can get the rest of that graph. And then later on, after we review this one, we're going to say, I wonder what it would look like if you actually did consider air drag, which would be a bit more realistic. Okay. Now it's going to start off at the same point. At time 0, it can have 0 speed because you're still just dropping it. Okay, so they start out the same. Okay, but then one of these is going to look, well, they're going to look different by the end of this, right? All right. So everybody should definitely get the graph on the left because it's been in your come up in your notes a few times now. Showed up on the quiz. Okay. All right. So for no air drag, did everybody just draw this just like that? You guys just did that, right? Okay. You guys remember that second kinematic equation? The speed it picks up to is the speed it starts with plus GT. Right. If it starts from 0, then fuck that. Okay. So, isn't the slope of this G? Right. Just about 10 meters per second squared on Earth. Right. Guess what that? Okay. However many seconds it tick by, tick, 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 tick. So like it's falling for 3 seconds. 3 times 10 is 30 meters per second. Okay, you guys remember all that. Right. But now let's switch over and put in some air drag. Now, we've just been thinking about the situation of suppose you got a super tall cliff and you got something that's been falling for so long that it's reached terminal velocity. I'm going to put terminal velocity on here. Call it V terminal. Right here. Suppose it's been falling for a long time. Gonna give you guys some time to think about that. Don't want to give you guys 2-minute hints. So you guys can figure that out. What's that graph going to look like? Aha, winner. All right. Okay, some of you guys getting this? Okay. So I think you guys are saying it's gonna start out pretty well the same. Because if this has only been following for like a fraction of a second, the air drag hasn't really built up much. So it starts out looking the same, right? Okay. So got your slope of pretty close to G and right? But you guys know that after a long time, it's eventually going to reach this horizontal asymptote, isn't it? Horizontal asymptote, right? Where after it's been falling for like 10, 11, 12 seconds, it's not really speeding up anymore, right? So we're going to connect these things kind of like this. Kind of taper off. Ah, guys get that? And then if there's like more seconds, like more paper off to the right, it's just going to fall at constant velocity all the way down to the ground, isn't it? Right? You guys get that? Okay. Now I can tell you guys the mathematics of this curve is really tricky. I saw the mathematics of this curve solved once when I was back in college. There's a class I took, a math class called differential equations, and you took that class after calculus 3, and yeah, saw it solved. Ooh boy, survived that. And here I am today to tell you generally about the shape. There you go. All right, so back over to PowerPoint. All right. Ooh. So just went a little faster here. Boat moving through water at constant velocity. All right. So it's got a weight down. There's a buoyant force pushing up. There's a maybe an applied force, maybe the propellers against the water pushing it forward, and probably a drag force pushing it back. Okay. Notice how all those forces cancel out. The verticals cancel, the horizontals cancel, because I specified constant velocity. Okay. So that boat would be in equilibrium, wouldn't it? Constant velocity through the water. How about 3 forces acting on an object to put it in equilibrium? So I have to go a little fast with this because it's got just enough time to do what I want here. But here's a good puzzle question, right? There's probably 100 different answers to these. So let's look at 2. Do you think you could do 3 forces equal magnitude, 120 degrees from each other? Right? Hey, isn't that one you did for your spring scales lab? You guys did one. Just turn that upside down, right? How about this? What if there's 10 newtons up and 5 and 5 down, right? You know, there's probably like 100 different things you could do, at least, right? Okay, parachuter before terminal velocity. Do you think there's a weight down and the drag force is building up like that? Okay, and then that parachuter right there, is that parachuter still accelerating? Yes, because there's a net force. Okay, it's not the full rate of gravity, but still picking up speed. So still picking up speed. Do you think that drag force is picking up more? Okay, until eventually, next slide, terminal velocity. Those 2 forces are going to balance. Okay, do a couple more things here with you guys. Got just enough time to fit this in. So I'm going to give you guys a little more details, but actually I'm just going to cheat a little bit. I'm going to copy it from last class. Okay, here you go. Okay, what is that drag force related to? Well, I've seen different versions of this formula, so I'll give you guys this anyway. Okay, there's the coefficient of drag. Looks like an aerodynamic thing. You guys know how if you're, say, an aerospace engineer building planes or rockets, or how about cars, right? Different cars design have different aerodynamics. Right? That's built into this coefficient of drag. Density of the surrounding fluid, air in this case. If I took this parachute through the water, water's 1,000 times the density of air, 1,000 times the drag force. Right? Area, this cross-sectional area. So that's why you want your parachute to have really big, touch a bunch of air. Right? And the speed squared, interesting. So if you built up to like 3 times the speed going down, you'd actually get 9 times the air drag. 3 times the speed is 9 times the air drag because the speed being squared. The drag is proportional to the square of the speed. Okay, you guys get that? Okay. Now you guys won't have to memorize this. Probably won't ever come back in this class. I don't know. Okay. But what is good to do is to be able to look at this formula, whether you see this in a textbook or on Google or on Wikipedia or some slightly different version of this, be able to pick this apart. Say, okay, well, I know what these variables mean and what the relationships are between these variables. Okay, we're gonna do one more for today. All right, one more free body diagram. Here it is. Rocket moving constant velocity, 10,000 meters per second in deep space. Sure, just screaming through deep space, 10,000 meters per second. What's that free body diagram look like? Wait a second. There's no friction in space. That would be interesting to think about, right? See, if there's no friction. Okay.
All the forces in deep space are negligible.
Right, yeah, no friction. There's no gravity force.
So we make constant velocity, so there's no force that's going to act against
Ah.
it if it were to accelerate. Therefore, it's like accelerating with the constant velocity.
Yeah,
So
okay,
it looks just like this.
that's it, that's it. That's the answer. Yeah, you got it. You're looking at the answer right there. You're looking at it right on that screen. There are no forces on that rocket. Wait, if there's no force on the rocket, what's keeping it going?
It's inertial acceleration.
Inertia. Yeah, right. Just whatever's going, right? If there's no forces on it, it's just gonna keep going. All right, there you go. All right, yeah, just in time. That is a wrap on today.